There you go. Okay, so there is a relationship between the moment and the curvature. Okay, so that relationship we need to derive. Okay, so that is called as the moment curvature relationship. Okay, so please take down the next point or next heading, that is moment curvature. Moment curvature relationship. Okay, now let's see what is this moment curvature relationship. Okay, so we already know that the moment is given by m equals to sigma y into z minus z0 divided by 3. This already we know. Okay, here you can see we have already derived that part. Okay, so now what we need to do, we need to put the value of z0. Okay, so if we put the value of if we put the value of this z0, so that can be written as equals to sigma y into z minus, instead of z0 we can write b into y0 square divided by 3. Okay, now what is y0? Y0 is the distance between the neutral axis and the extreme fibers. Okay, and we already know that phi. What is the value of phi? Here you can see this one is the moment. This one, phi equals to sigma y by e into y0. Okay, so that we can write it here. So that we can write it as, so it is phi equals to sigma y divided by e into y0, we already know, or we can write this instead of y0. This implies y0 equals to e into phi divided by sigma y. Okay, right? So now this value we will put it here. So this implies the moment can be expressed as m equals to sigma y into z minus b by 3 into e phi by sigma y. This is whole square. Okay. Now dividing, let us divide. I'll tell you the reason why we are dividing and all. Okay. So now if divide, okay, let's divide this equation. Let us say I'm calling this as equation 1, suppose I, or equation I. Okay, so divide equation I by my. Okay, now what is my? So my equals to, we already know it is sigma y into s. Okay, so we can write m by my equals to z by s minus b into sigma y square divided by 2 into s into e square phi square. Now who is this disturbance? Vijay Kumar. Okay. right? Now with y0 equals to d by 2, where d is the, where, what is d? D is the depth of beam of rectangular beam. Okay, depth of rectangular beam, and phi equals to, if we take phi equals to pi y, that is at pi at yield. Okay, if we take that, and z equals to bd square divided by 4, s equals to bd square divided by 6. Okay, and this phi equals to pi y we have taken, so that equals to sigma y by e into, sorry, e into y0. Okay, if we use all these values and we put it, okay, let us say this is equal, this one I am considering as equation 2. Okay, so putting all these values, equation 2, we have, now you can check, I'm directly putting that value, you can check it on your own. So m by y equals to 3 by 2 into 1 minus 1 by 3 into 5 y divided by pi whole square. Okay, where this pi y we are calling it as curvature at yield, y e I e, curvature at y e I l t. Okay, curvature at yield. Okay, now let's see the relationship for that one. Okay, so if you plot it graphically, if you plot this one graphically, now which one I'm talking about to plot graphically. So if you plot this one graphically, so this is phi by phi y, and this is m by my. Suppose if you plot this one and this one in this direction. Okay, so there will be zones. Okay, now at zone 1, sorry, no, zone 1 will not be here, it will be just a little bit above, so zone 1 will be somewhat here, and here it will be, this is for zone 1. Okay, next somewhere here it will be in zone 2, next somewhere here it will be zone 3, and somewhere here it will be zone 4. Okay, and the corresponding value, it is 10 here and it is 1.5. Okay, now one special case can be done. Okay, now this is for the rectangular section 1. Okay, we can develop the, or we can write it directly like this. So similarly, the relationship between m and psi, m and psi, phi, sorry, mi phi can be determined for I section, for an I section, or I section beam, or I beam, you may write, for an I beam. Okay, now for this I beam there will be again two cases. That is, the first case is for yield zone within the flanges. You just remember these formulas, no need to go for deriving and all. If you want, you can go and derive. Okay, so if we talk about for yield zone within the flanges, this is one word, within the flanges, it is m by my equals to phi by phi y into 1 minus bd square by 6s plus bd square by 4s into 1 minus 1 by 3 into phi y divided by 5 whole square. Okay, next case is for yield zone extending into the web. Into the web means into the web of I section. Okay, that will be m by my equals to, it is mp by my. Okay, that is the plastic moment by the yield moment minus tw into d square divided by 12s into phi y divided by phi square. Okay, now this one thing it is to be noted, that this tw is the, it is like this tw point, so it is thickness of web. Okay, right, now we have another concept called as the shape factor. Okay, So please write this one. Next concept is the shape factor. Okay, so from this shape factor part or topic, you will definitely get one numerical question. We'll do that based on that. Okay, so now what is the shape factor? Okay, so the shape factor is the ratio of the plastic moment. Okay, please pay attention. Shape factor is the ratio of the plastic moment and the yield moment. Okay, this we have already seen this one. So that we call it as the shape factor. This I can write it here directly, shape factor. Okay, but let us write it in sentence here. Okay, so you can write that the ratio of plastic movement plastic movement capacity, that is MP we call it. Okay, MP to the yield moment, that is My, is called the shape factor, is called the shape factor for बाबा टिके क्लास रे अछि धनो हैला टे छाड़ी कॉल कर so is called the shape factor for a section. Okay, okay, so now you may ask, sir, what this shape factor represents. Okay, so this factor, it represents the increase of strength due to the plastic moment capacity. Now okay, okay. Let us say it is shape factor. Suppose I am representing it as SF. SF equals to, I am saying MP by My. Okay. Now, when the value of SF will be more, or the shape factor will be more, when the value of yield moment, then it is going to be more. Okay. So this shape factor, so here you can write, what is this shape factor represents the increase in strength due to the plastic capacity of the structure. And guys, can you hear my voice properly?
Sir, your voice is
No,
breaking,
sir.
sir.
No, sir.
Now also you can't hear my voice?
Sir, your
Can
voice is
you
not
hear my
clear.
voice?
No, sir.
My
Hello.
voice. Yes. Okay, one
Fine, sir.
moment. Okay. Now it is fine, huh?
Yes, sir.
Yes, sir.
Okay. Many of you are okay. So now the factor is
Sir, again,
the
again, it is happening like
Again, your
this.
voice is breaking.
okay. Now is it audible properly?
Yes, sir. Fine.
Okay. So now let us okay. Let us find the shape factor for the rectangular section. Okay. Now just tell me. We'll take a small, just one mark question or 1 mark small question. Okay. So let us say this is SF. Okay. For rectangular section, I'm doing. Rectangular section. Okay. Now, so the shape factor will be MP by MY. Okay. Now, from your notes, please tell me what is the value of MP? MP. Go back and check what is the value of MP for rectangular section. MP.
Sigma YZ.
Sigma y into Z. Now, what is the value of My? From your notes, please see that and tell me what is the value of My? The yield moment, it is
Sigma YS.
sigma y
Sigma
into S.
into S.
Yes, sigma y into S. Okay, now the sigma gets cancels out and this becomes Z by S. Okay, now what is the value of Z again? Please check your notes and tell me what is the value of Z for rectangular section. Here you have already
BD
done.
square by
Here.
BD square by 4, sir.
Yes, BD square by, it is BD square by 4 and S, the value of S is BD square by 6. Okay. So if you do that, so it becomes 1.5. Okay. So the shape factor for a rectangular section is 1.5. Okay. Now we do have, okay, so let us have a table. Okay, so if the section is rectangular one, then the shape factor can be of 1.5. Okay, now let us have, so okay, before we go any further, now just tell me one thing. Now the shape factor, it all depends on the geometry of the section. So here we can write, here take an important point. You can write the shape factor depends on, the shape factor depends on the geometry of the section only. Okay, see, there is no other components here, only the breadth, depth. Okay, now for different sections, okay, let us say I'm making a table, types of section, okay, means types of cross section, okay, or types of section and their shape factor value. Okay, now if it is a diamond shaped, for a diamond shaped one, this values have been already calculated, no need to calculate, it is better if you remember these values. Okay, so if it is a diamond shaped one, the shape factor is 2.0. If it is a rounded one, or round shaped, then for this it is 1.70. Next, for rectangular one we have already calculated, so let me write it once again. RECTANGULAR, rectangular shaped, we have calculated this now, it is already 1.5. Okay, now if it is a tube shaped, SHAPED, if it is a tube shaped, then it is 1.27, and if it is an I section, then the value, it varies from 1.12 to 1.20. Okay, is it fine? Is it clear now? This again. Okay, so now before we go to the or before we end, okay, before we go, let us write one question which we are going to solve in the next class. Okay, and then we will come to, after that we have the plastic hinge and some other. Okay, so right. So before you go, please write the question. The question is, determine the shape factor of triangular section. Okay, so we have seen for that for diamond section, diamond shaped rectangular shaped, rounded shaped, rectangular shaped, tube shaped, eye section we have seen. Okay, now let us determine the shape factor for a triangular section. Okay, now tomorrow I will give you the shape. So how which type of triangular one, whether it is an equilateral triangular one, whether it is isosceles one, whether like that. Okay, or it is a right angle triangle one. Okay, that we will discuss in the next class. Okay. Now, any doubts you have till now?